Hello, in this lecture we will answer on two questions. The first question is to find out the area of the semicircle that is inscribed by a quarter circle, and the second question is to find out the area of this angle theta, that is one angle out of three angles of the right triangle ABC. Okay, so we'll start with the first question. In the drawing, we have a semicircle that is inscribed by this quarter circle. We know that the radius of this semicircle is equal to 3 units, and we want to find out the area of this semicircle that is inscribed by the quarter circle. So we will define the center of this semicircle as point O, so point O, this point is the center of the semicircle, and I will also present to you a new rule. This will be rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I read rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle, and we know that the center of this circle is at this point O, and we also have tangent AB to this circle here. This tangent AB is tangent to this circle at this point M. Point M is the point of tendency. The point of tendency of tangent AB with this circle. So according to rule number 1, here we have the radius that we define as R. So you can see in the drawing that the radius OM, it is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Again, a tangent to a circle, that is to say, tangent AB, is perpendicular to the radius, is perpendicular to the radius OM. Which radius? The radius that is drawn to the point of tendency. Because of the fact that the radius OM, it is drawn to the point of tendency, that is to say, to point M, that is the point of tendency of tangent AB with this circle, then the tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? So we can implement rule number 1 in our drawing. Here we have and the center of the semicircle is at point O. From point O we will draw radius, the radius of the semicircle that will be defined as R. We will draw it to the point of tendency here. So here this is point A, point B, point C, point D, point E, point F. So OB is the radius of the semicircle, that is to say, it is equal to R, and we have the radius OB that is drawn to the point of tendency. That is to say, the radius OB, it is drawn to point B, that is the point of tendency of tangent AC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, according to rule number 1, the tangent AC will be perpendicular to the radius BO. So AC is perpendicular to BO, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, from point O, the center of the semicircle, we will draw the radius to the point of tendency. Here this point is point H. So from point O, we will draw the radius to the point of tendency, that is to say, to point D. Point D is the point of tendency of tangent CH with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent CH will be perpendicular to that radius. So CH is perpendicular to OD, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay? According to rule number 1, of course, and because of the fact that ACH is a quarter circle, then point C must be the center of the quarter circle, and angle ACH must be equal to 90 degrees. Okay, this is true for all the quarter circles. This is always will be the center of the quarter circle, and this angle must be equal to 90 degrees. So in quadrilateral OBDC, we have 3 right angles. We'll repeat again, in quadrilateral BOCD, we have 3 right angles. The sum of 3 right angles is 3 times 90, it is 270 degrees, plus the size of the 4th angle, that is actually angle BOD, this angle BOD, In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? So here we will subtract 270 degrees from this equation. And we'll get that the missing angle, angle BOD, is equal to 360 degrees minus 270 degrees. It is 90 degrees. Okay? So we found out that the missing angle is a right angle. It is equal to 90 degrees. This angle equals to 90 degrees. It is a right angle. Therefore, all the angles inside quadrilateral BOCD are right angles, and we know that any quadrilateral, that all of its angles are equal to 90 degrees, it must be at least a rectangle, if not a square. So we will relate to quadrilateral BOCD as a rectangle. Okay, we can write down that quadrilateral BOCD is a rectangle. And we have also rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. Okay, I will write it down. Rule number 2 states that the opposite sides of a rectangle are equal to each other. I will read rule number 2 again. According to rule number 2, the opposite sides of a rectangle are equal to each other. So actually, the opposite sides of rectangle BOCD are equal to each other. That is to say, side BO must be equal to side CD. BO equals to CD. BO equals to CD according to rule number 2. But we have already found out that side BO equals to R. It is the radius of the semicircle. So we can write here that BO equals to R. And from this equation, R equals to BO equals to CD, we will derive that CD is also equals to R. CD is equals to R. Here, CD equals to R. Likewise, according to rule number 2, we will get that OD must be equal to BC. OD must be equal to BC according to rule number 2. But OD equals to R. It is the radius of the semicircle. OD equals to R, and from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. Here BC equals to R. So we actually found out that all the sides of quadrilateral BOCD are equal to each other, and all of its angles are right angles. Therefore, quadrilateral BOCD is not a rectangle but a square. So we can write down that quadrilateral BOCD is a square. Okay, quadrilateral BOCD is a square. In the next step, We will join points O and C together by a straight line. And we'll find out the length of diagonal OC. Diagonal OC is the diagonal of square BOCD. We will find out the length of diagonal OC by implementing the Pythagoras theorem on the right triangle ODC. We will implement the Pythagoras theorem on the right green triangle, triangle ODC, and in this way we will find out the length of line segment, the length of diagonal OC. Okay? We'll find out the length of diagonal OC in terms of R, of course. Not any number, but it is in terms of R. That is the radius of the semicircle. So here, according to the Pythagoras theorem, if we relate to the green right triangle, triangle OCD, in the green right triangle, triangle OCD, by PT is the abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, according to the Pythagoras theorem. So we get here that the square of the hypotenuse is CO square. CO square equals to OD square plus CD square. So here, I will repeat again, according to the Pythagoras theorem, CO square equals to OD square plus CD square. Here, CO is the missing variable, so we will leave it as it is. So CO square equals to OD square. OD equals to R, so OD square will be equal to R square plus CD square. CD equals to R, so CD square will be equal also to R square. R square plus R square is 2R square, so we got that CO square equals to 2R square. We will take a root out of this equation and we will get that the value of diagonal CO, the diagonal of the square, it is equal to square root of 2 times R. Okay? CO equals to square root of 2 times R, so we can write here that diagonal CO square BOCD equals to square root of 2 times R. In the next step, we will extend diagonal CO by a straight line until it touches the quarter circle at this point, point S. So, what is the length of line segment OS? It is very easy to see from the drawing that the length of line segment OS, is actually equals to CS minus CO. And if